Hello everyone. In this video, we are going to learn about linear regressions. So this is the reading list. I have similar chapters from two textbooks that are all uploaded on Course Connect. The first one is Intro to Statistical Learning, Chapter 3. This is a bit mathy, but if you're interested and want to learn a little more, I would recommend this one. And Learning Statistics with R, Chapter 15, is a more intuitive take on this topic. This is a wide, this has a lot of stuff in it, and there's a lot to unpack, but I'm going to give you an overview of what this topic is. So, to begin with, as I said, today we are going to explore linear regressions. This is one of the most useful tools in our statistical toolkit. Linear regression is, to put it simply, it's a way of modeling relationships between variables. So think of it as finding the best straight line through your data points. This approach helps us understand how one thing affects another. When we use linear regressions, we're looking at the relationship between a dependent variable, the one that we want to predict, and one or more independent variables, those are our predictors. For example, if you want to predict house price based on square footage, then price is our dependent variable and square footage is our independent variable. What makes linear regression special is that it assumes this relationship to follow a straight line or in a higher dimension a plane or a hyperplane. But now, while real-world relationships are rarely perfectly straight lines, this simplification is incredibly useful and often gives us a very good approximation that is easy to understand and interpret. And even though it's one of the oldest statistical techniques, linear regression still remains extremely powerful, and sometimes, as they say, simplest tools are the most useful. Let's break down the idea of linear regression with a simple equation. So we have this equation over here, y equals beta naught plus beta 1 x plus epsilon. These are fancy Greek symbols, but don't worry about it. So beta naught is the intercept, okay? So what this means is that this is the value of y when x equals 0. Think of it as a starting point on the y-axis. Beta 1 is the slope. It tells us how much y changes when x changes by 1 unit. This is really what we care about. It shows us the relationship between our variables, which in this case are y and x. And the epsilon? Epsilon is the error term. It represents everything our model doesn't capture because relationships are never perfectly linear. So you cannot throw everything in the model. You cannot capture everything that you want to capture. So epsilon takes care of that. Linear regression comes in two main flavors, so to speak. One is what we call the simple linear regression, which uses just one single predictor. And the other is a multiple linear regression that uses two or more predictors. So think of this house price example. If you want to fit a single linear regression, we would regress price on just one predictor, which in this case is square footage. But you can think of a scenario where this is not true, and it's easy to see that this is not really the right way to approach because house price depends not only on square footage, but also on several other factors, and you can throw them in to make it a multiple linear regression model, which has square footage, number of bedrooms, neighborhood, and any other housing variable that you might think of. And when we when we deal with a multiple regression model, it typically spits out something like this. So we have an estimated value of price with some numbers. So when we take this model and we take this to the data and we end up with this number, we estimate the beta naught to be 50,000, beta 1 to be 100, and beta 2 to be 2000. So the question is, what does it mean? It means that, so we are typically interested in the beta 1 and the beta 2. Beta naught is usually not something we focus on. So beta 1 equals 100 means each additional square foot is associated with a $100 increase in price, holding age constant. And this is very important over here. So in other words, if we increase the size of the house by 1 extra square foot, then according to this model, we can predict the price to go up by $100 on average, assuming the age does not change. Beta 2 equals negative 2000 means each additional year of age is associated with a $2,000 decrease in price, holding size constant. And I kept saying this, holding other factors constant. And so let me talk a little bit about that. This idea of holding other factors constant is extremely powerful, but it means that we can't simply visualize the relationship in a two-dimensional plot anymore. So we need to interpret the coefficients carefully in its proper context. And this is again a summary of the regression coefficients. So beta naught is the expected value of y, or the average value of y when all predictors are set to 0. And the reason why we don't really focus too much on it is because this number in itself doesn't make any sense. Because if all predictors is equal to 0, then what is the point of building a predictive model in the first place? So it's just there on the side. What we are more interested in is the slope coefficients, the beta 1s, the beta 2s, beta 3s, whatever number of betas you have in the model. And in a simple example, so if you want to fit a single linear regression model and you have this equation fitted, y hat equals 60 plus 5x, which means that for every unit increase in x, which in this case is the score, this is a typo, your predicted value of y increases by 5 points on average. What it also means is that not every time you increase the value of x by 1 unit, your value of y will go up by 5 units. It won't happen every time. Sometimes that increase will be more than 5, sometimes that increase will be less than 5 as well. But on average, if you increase the value of x by 1 unit, on average, the value of y will increase by 5. So that's all this regression means. And we already talked a little bit about multiple regression coefficients. The key thing over here is that when you're interpreting the beta 1s and the beta 2s individually, make sure to keep in mind that when you're interpreting the coefficient on x1, which is the first predictor, you are holding all the other predictors constant. So that's what that number means. So how do we actually find the best line through our data? That's where the method of least square comes in. It's a technique that has been helping statisticians since the early 1800s, and the intuition is pretty straightforward. It means that for each data point we have, we calculate something called the residual. This is simply the difference between what our model predicts and what we actually observe, the vertical distance between our line and the point. So in this figure, as you can see, this is a line that we have fit, and there are 3 data points that we have. Some of the data points are closer, some are far off, and this vertical gap between each point and the line is what we call the residual. And what we're looking to do is find a straight line like this one in blue that minimizes the sum of these square residuals. Why do we square them? We square them for 2 reasons. One, it penalizes larger errors more heavily, and it ensures that the errors are and it ensures that the positive and negative errors don't cancel each other out. This method gives us mathematically an optimal solution, the unique line that best fits our data according to this squared error criterion. It's elegant, it's efficient, and till now it has stood the test of time for very, very good reasons. So now let's look at how actually we calculate the parameters for our best fitting line. The formula kind of looks intimidating at first, but the ideas behind them are quite intuitive. For a simple linear regression, the formula for our slope, beta 1, shows that it is essentially the covariance between x and y divided by the variance of x. What does this mean? It means that the beta 1 hat, which is the estimated value of beta 1, captures how x and y move together relative to how much x varies on its own. The formula for our intercept, beta naught, is even simpler. It is just the mean of the dependent variable minus the slope times the mean of x. It ensures that our line passes through the points of averages. Do not have to worry about memorizing these results, like the exact formula, that's not the point. What's more important here is understanding what they represent. They are giving us parameters that help us minimize the sum of squared residuals. Now the good thing is all modern statistical software handles these calculations for us, so we don't need to do them by hand, but understanding the underlying equation helps us grasp what is happening under the hood. We are finding the line parameters that are making our model as closely as possible fit the data according to our least square criteria. So once we have fitted our model, a natural question is, how well does this actually fit the data? Right? That's what we care about. We want to fit a model that fits our data well. So we need a criteria to evaluate that. And that is where R squared comes in. R squared is a measure of proportion of variance explained by our model. It ranges from 0 to 1, or if you prefer percentages, 0% to 100%. A higher value indicates a better fit. In other words, our model is explaining more of the variation of the dependent variable. The formula for this measure shows that it equals 1 minus the ratio of the residual sum of squares to the total sum of squares. Residual sum of square represents what our model does not explain, while total sum of square represents the total variance in y. So this ratio tells us what fraction of the variance remains unexplained, and subtracting from 1 gives us the fraction that is explained. Intuitively, our model fits perfectly so think of it in this way. If our model perfectly fits every data point that we have, then R squared would be 1 or 100%. That means that we have explained all the variance of the dependent variable through our model. If our model does no better than predicting the mean of y for every observation, R squared would be 0 because we have explained none of that variance. So R squared gives us a standardized measure of the fit that's easy to interpret, making it one of the most commonly reported statistics for regression models. It helps us quantify just how much of the pattern in our data we have managed to capture. But it's not a perfect measure. While R squared is useful, it also has a quirk that can lead us astray when we are comparing models. And that quirk is, it always increases or at least stays the same as we add more predictors. So think about this. Even if we add variables that have no relationship with what we are trying to predict, R squared will still go up. This happens because each new variable can explain at least a teeny tiny bit of the variation in our data just by chance. And this creates a problem because when we are comparing models with different number of predictors, if we simply choose the model with the highest R square, we will always end up with selecting the model that has the most number of predictors. And that is not always the best approach. Look at this graph here. So suppose if we increase the number of predictors, the true quality of the model first increases and then it declines. So suppose this is the true nature, so suppose this is the true link between the model quality and the number of predictors. What we have over here is that if we just look at the R square, it will monotonically increase. So as you throw in more predictors, useful or not, the gap between your perceived measure of goodness of fit versus the actual quality of the model, that gap will go up. So this limitation tells us that we need a better measure or we need something to fix this problem. And that brings us to the next slide. To address this limitation of regular R square, we have an alternate version of this called the adjusted R square. This version penalizes the model for including too many predictors. The formula looks similar to R square, but with an adjustment factor that accounts for the number of predictors, P, and the number of observations, N. This adjustment ensures that adjusted R square only increases if a new variable improves the model more than would be expected by chance. So if you throw in a predictor and it is increasing the R square, but it's only happening by chance, then adjusted R square won't go up, even though the normal R square would. And the beauty of this adjusted R square is that it can actually decrease when you add unhelpful predictors in your model. And this makes it much more useful for comparing models with different number of variables. So let's think about what adjusted R square is really doing. What it is doing is that it's balancing model fit against model complexity. It is helping us avoiding a problem of overfitting, where we create a model that matches our training data but will not generalize well to new data. So when you're comparing regression models with different number of predictors, adjusted R square gives you a more honest assessment of which one is truly better at capturing the underlying pattern of your data. And here's an example of that. So suppose you take the house price example and you fit three models. In the first model, you have only size of the house. In the second model, you have size of the house and how old the house is. And in the third model, you add those two and just throw in 8 absolutely garbage variables in the model that you know with certainty has no link whatsoever with the price of the house. What you can get is the R square will keep on increasing from 0.65, which means 65% of the variance in price is explained by the size of the house. That R square will jump up to 0.68 when you throw in age, and will jump up to 0.71 when you throw in those 8 irrelevant variables. But if you look at the adjusted R square, between model 2 and model 3, adjusted R square actually declines, which tells you that model 3 is actually a worse model, even though it has more number of predictors than model 2. And this makes sense because all that is new in model 3 as compared to model 2 is these 8 jump variables that have no link whatsoever with the model that you're looking at. There's another important statistic related to R square, and we kind of talked briefly about that, so let's talk a little more, is the residual sum of squares. It is a fundamental concept in regression analysis. RSS measures the total discrepancy between our observed data and our model's predictions. It is calculated by taking each residual, that is the difference between the observed value and its predicted value, squaring it, and then summing all these squared residuals up together. This concept is the foundation of least square estimation. We choose our model coefficients that specifically minimizes RSS. It is also used to calculate R square and hence adjusted R square as well, as we saw earlier, and it plays a key role in calculating the standard errors of our coefficients. RSS appears in many model selection criteria like the AIC, which is the Akaike Information Criterion, BIC, which is the Bayesian Information Criterion, and Mallow's CP. So there are different model selection criteria. We will talk about that in a separate video. And it is also directly related to the estimated variance of our error term. Which is also an important parameter for statistical inference. So think of RSS as a measure of what our model has not explained. A smaller RSS means our model is doing a better job of capturing patterns in the data. It is the most direct measure of our model fit, and that's why it is central to so many aspects of regression analysis. So far, we have focused on continuous predictors, but we also often deal with another type of predictors called categorical variables like gender, product type, region. Linear regressions can handle these too through a technique called dummy variables. With dummy variables, we convert these categories into zeros and ones. For example, for gender, we might create a variable that equals 1 if the person is female, 0 I apologize if the recording got interrupted in between. So let's take this slide from the top again. So we have worked with continuous predictors so far, which is with variables like size of the house, age, price. But we often deal with data that are more like categories, like gender, product type, or region. Linear regression can handle these too through a technique called dummy variables. With dummy variables, what we do is that we convert categories into zeros and ones. For example, if for gender, we might create a variable that takes the value 1 if the person is female and 0 if male. Our model then becomes y equals beta naught plus beta 1 x plus epsilon. The model remains the same, but interpreting this coefficient now becomes a little different. And so now beta naught represents the expected value of the reference group. So if you have a gender, if you take the gender example, so x equals 1 if the person is female, and x equals 1 and 0 if the person is male. Beta naught is the expected value of the reference group, and the reference group is that group for whom the value 0 is assigned. And beta 1 represents the difference between groups, is how much higher or lower the expected value is for females compared to males. So you can think of an example where you're looking at wage gap across gender. So y is your wages and x is gender, which is equals 1 if the person is female. The beta 1 then will capture what is the difference in the wages for women as compared to men. This is a very simplistic scenario, but this is the starting point for all these kind of studies. What about variables that have more than 2 categories? We then need multiple dummy variables, specifically one fewer than the number of categories. For example, if we have regions, so if you want to create a dummy for regions, north, south, east, and west, we create 3 dummies and leave one region out, as the reference. So I can create a dummy for north, south, and east and keep west as the reference, or any other combination. So in that case, those coefficients would be interpreted as difference from the reference group, which is west in this situation. This approach allows linear regressions to incorporate categorical information, making it even more versatile for real-world data analysis where many important factors are numeric. Let's walk through a concrete example. So suppose we are looking at the association between miles per gallon, MPG, and the type of transmission AM. So AM is a dummy which takes the value 1 if the transmission type is automatic and 0 if the transmission type is manual. And if we run the regression, suppose we end up with this regression. So MPG hat is 17.14 plus 7.24 times AM. This 17.14 means that manual transmission cars on average have a fuel efficiency of 17.47 miles per gallon. So this beta naught is that for the reference group. Beta 1 hat, which over here is 7.24, means that cars with automatic transmission have an MPG that is 7.24 higher than manual transmission cars on average. Not all automatic transmission cars have a 7.24 higher MPG. Some can have higher, some can have lower, but on average, automatic transmission cars have a 7.24 higher MPG than manual transmission cars. And therefore, the total effect of the automatic cars is 17.14, which is the baseline for in this model, plus 17.2 plus 7.24, which is 24.38. So if you want to look at the total MPG of automatic transmission cars, you need to take the baseline and add the difference to that as well. So beta naught plus beta 1. And this is what we get over here. So this is 17.14, which is the beta naught. And you can see that the estimated effect of being automatic transmission is somewhere over here. This difference is 7.24. So far, we have assumed that each predictor has an independent effect on our outcome. But in real life, the effect of one variable often depends on the value of another. And that is where interactions come in. Let's consider the MPG example again. Maybe the effect of engine displacement on fuel efficiency differs depending on whether the car has an automatic or a manual transmission. Powerful engines might be more efficient. Others might work better with manual. We don't know. So we find that out. So we model this using interaction terms with a term and we want. So this interaction term is basically this beta 3 over here, which is an interaction between the displacement and the car being manual. So beta 3 captures the difference in the displacement between automatic and transmission cars for a given value of displacement. So in the empty cars, when I run this regression, I get beta 3 to be negative 0.03, which means that cars with manual transmissions have 0.03 miles per gallon less mileage than those with automatic transmissions on average for a given level of displacement. And graphically, it basically allows us to estimate two regression lines. One, so in the x-axis we have displacement, in the y-axis we have miles per gallon, and this reddish orange line is the association between displacement and MPG for manual cars, and the blue line over here is the same relation but for automatic transmission. And this gap over here is what we get. Okay, there is a slight chance that I've messed up the coding over here. So this gap should have been equal to, either this gap should have been equal to negative like 0.03, or this number is off. I'm sorry, I will fix this later, but in general, this gap, this beta 3 hat, is the vertical distance between these two lines. That's what we are trying to do. Real world relationships are often not linear, but that doesn't mean that we cannot use a linear regression to model them. We just need to be a little more creative with our variables. One approach is to use polynomial terms. For example, instead of using y equals beta naught plus beta 1 x plus epsilon, we might use y equals beta naught plus beta 1 x plus beta 1 x squared plus epsilon. This allows a regression line to curve, capturing nonlinear patterns. We can use other transformations like log, exponentials, etc. And we can play around with that as much as we want. So the key thing is, just because this is a linear regression model, it doesn't necessarily have to be the case that the variables are also included linearly. You can have nonlinear variables in a linear regression setting. There are some common issues that I want to talk about. The first is heteroscedasticity. It's a fancy term, sounds very complex, but in reality the idea is very simple. It means that the variance of our error term isn't constant across observation. So if you see a typical scenario for heteroscedasticity, you will see that if you fit a straight line, and you plot the data points as well, it kind of looks like an exploding situation. So the higher is the value of x, further the points are from the fitted line, as compared to a homoscedastic situation where for all values of x, the data points are kind of equally distant from the regression line. The reason why we care about heteroscedasticity is because it doesn't affect the point estimates. So the betas that you get, the estimated associations, they don't change, but the standard errors take a hit. So which means that if you have a data with potential heteroscedasticity, and if you don't account for that, you will end up with less precise estimates of your association and will potentially make incorrect conclusions about which variables are significant. The good news is that heteroscedasticity is so common in real-world data sets that statisticians have developed straightforward solutions. In fact, if you're working with a data set where you find no heteroscedasticity, you should be worried, because heteroscedasticity is a pretty normal and common event with real-world data sets. The second safety check is serial correlation. This happens when the error terms in our models are correlated across observations. Think of it in this way. Sometimes information from the past continues to influence the present. This is especially common in time series data or longitudinal studies where we track subjects over time. For example, if we are analyzing unemployment rates, then a shock in a particular month is likely to affect subsequent months as well. This means that our error terms are not independent of each other. This matters because, just like heteroscedasticity, this issue affects the standard errors or the precision of your estimates. There are solutions. One approach is to use something called the Newey-West standard errors, which provide robust estimates without changing our coefficient values. This is particularly useful when we are not sure about the exact correlation structure of the error term. Another approach is to add lag-dependent variables to our model. By including past values of our outcome as predictors, we often capture the underlying patterns that were causing the correlation of the error terms. There are several others as well, but these are two most commonly used methods. So Let's take a step back and consider why these checks matter. Both heteroscedasticity and serial correlation affect the standard errors of our estimates. But as I said, it doesn't affect the point estimate, so it doesn't change the value of association that you get. So why should we care about it? We should care about it is because when our standard errors are incorrect, all our statistical tests based on these errors become invalid. That includes t-test for individual coefficients or f-test for groups of variables. The consequences is that we might conclude a variable is statistically significant when it's not, or vice versa. We could end up including irrelevant predictors in our model or exclude important ones. In short, we risk drawing incorrect conclusions from our data. And these issues don't bias our coefficient estimate themselves, but our line still goes through the middle of the data point in the right place. The problem is we become less certain about how precise these estimates are, and in general, how reliable our results are. So that is why these safety checks are important. So I hope this was useful, and please let me know if you have any questions or you want something is not clear. Thank you.